My name is Kateryna Khalina, and I would like to represent my joint work with Larissa Fardigola about controllability problems for the heat equation in a half plane in the case of a pointwise control in the Dirichlet boundary condition. A mathematical control theory deals with the analysis and design of control systems. The control system is influenced by input data or control to drive it to a desired state at the output. The control system can be represented by differential equation dw by dt equals aw plus bu, where t lies in the interval 0t. The capital T is a positive constant. W is a state of the system. It maps the segment 0t to h, to the space h. U is a control. It maps the interval 0t to this h. H and H are Banach spaces. A and B are linear operators. Let us give definitions. Let U be the set of admissible controls. A state W0 is said to be controllable to a state Wt in a given time t if there exists a control U in U such that there exists a unique solution W to system 1, satisfies this initial condition and this end condition. That is, a state W0 can be derived to a state Wt in a given time t by using a control U. A state W0 is said to be approximately controllable to a target state Wt in a given time t if for each positive epsilon there exists a control U epsilon in U such that there exists a unique solution W epsilon to system 1, satisfies this initial condition and this condition. The norm of the difference between the W epsilon at the point t and the target state Wt is less than epsilon. That is, a state W0 can be derived to epsilon neighborhood of a state Wt in a given time t by using a control U epsilon. And controllability problems are as follows. To investigate whether a state W0 is controllable or approximately controllable to a state Wt in a given time t. Controllability problems for the heat equation were studied both in bounded and unbounded domains. There are many results, for example, in papers of Dardet, Hammer, Ervidoza, Leons, Mulf, Pedregal, Cabanilas, Canarsa, Martinez, Van Constantinople, Zoazua, and many others. But there are much less papers dealing with unbounded domains than papers dealing with bounded domains. Moreover, most of authors studied controllability problems for the heat equation controlled by an interior control, which differs from a boundary control. Besides, in most of papers, a control belongs to the space L2 was considered. Therefore, we study the case of unbounded domains and the case of L-infinity control. Consider the following control system in a half plane. The heat equation in a half plane controlled by the Dirichlet boundary condition at line x1 equals 0 under this initial condition. Here delta is Laplacian, t is a positive constant, u is a control. We consider it in L infinity of 0t. Delta subscript m is the direct distribution with respect to xm, m equals 1 or 2. The subscript 1 corresponds to x1 and the subscript 2 corresponds to x2. And this controllability problem is considered in spaces of Sobolev type. First, consider the Sobolev spaces. Let alpha be two-dimensional multi-index. For S from 0 to 3, consider the Sobolev space HS of R2. It is a set of all square integrable functions on the plane, such that for all two-dimensional multi-index alpha, its absolute value is not greater than s, implies that this mixed partial derivative of phi is also a square integrable function on the plane. And this space is equipped with the norm. The sum over all alpha, whose absolute value not greater than s, of squared L2 on R2 norms of this partial derivative, and all to the power of 1/2. We also consider the space of distributions H minus S of R2. It is the adjoint space with a strong norm. For m from -3 to 3, by Hm tilde of R2, we denote the subspace of all distributions in Hm of R2 that are odd with respect to x1. Let R plus be a half-axis. For S from 0 to 3, consider this space of Sobolev type, HS0 circled. It is a set of all square integrable functions on half-axis, such that for all two-dimensional multi-index, its absolute value is not greater than s, implies that this partial derivative of phi is also a square integrable function on half-axis or half-plane. For all k from 0 to s minus 1, the k's partial derivative of phi by x1 at the point x1 equals 0 is equal 0. And this space equipped with this norm, the sum of all multi-index alpha whose absolute value is not greater than s, of squared L2 on R plus time R norms of the partial derivative of phi, and all to the 1/2. And we also consider the space of distributions H minus S0 circled. It is a adjoint space with a strong norm. We also need the following subspace of Sobolev space. We denote it by italic HS for S from -1 to 1. It is the space of all phi belongs to HS tilde or of R2, such that there exists distribution G in S prime of R, and F equals partial dg by dx1 of modulus x. Here S of R is the Schwarz space of rapidly decreasing functions, S prime of R is a dual space, and by modulus we denote the Euclidean norm in R2. And let's return to our control system in a half-plane, system 2-4. We consider this control system in spaces of Sobolev type H minus L 0 circled for L from 1 to 3. That is, this state W maps the segment 0t to H minus 1 0 circled. The partial derivative of W by t maps the segment 0t to H minus 3 0 circled. And the initial state W0 lies in H minus 1 0 circled. Denote by capital W0 and W the odd extensions with respect to x1 of small W0 and W respectively. Then we reduce our control system in a half plane to this control system in the whole plane. The equation is the partial derivative of W by t equals delta W minus 2 delta prime subscript 1 delta subscript 2 multiplied by u, and the initial condition. Here the state capital W maps the segment 0t to H minus 1 tilde. A partial derivative of W by t maps the segment 0t to H minus 3 tilde, and the initial state W lies in H minus 1 tilde. We prove in our work that these two systems in a half plane and in the whole plane are equivalent. Therefore, we will further consider this control system in the whole plane instead of this system. For this control system in the whole plane, we we prove some main results. One of them is a necessary condition for controllability from the origin under the control bounded by a hard constant. Let T and L be given constants, positive constants. Let Wt lies in H-1 tilde of R2. If there exists a control U in L infinity of 0t such that its norm is not greater than L, and the null initial state W0 is controllable to the state Wt in a given time t, then Wt is an element of italic H-1, and the following condition holds. Condition 7, the double integral of this function dx1 dx2 is not greater than this constant. And here t1 is greater than t. We also reduce the controllability problems for the heat equation with a control bounded by a hard constant to Markov power moment problem. Let L and T be given positive constants. Let W0 and Wt both lie in H-1 tilde of R2. Denote by W tilde the difference between the target state Wt and the convolution of this function and initial state W0. Let condition 7 holds for W tilde. Condition 7 holds for W tilde instead of Wt. And let omega n be defined by this formula for n from 0 to infinity. Double integral of this function dx1 dx2 multiplied by this factor. Under all these conditions, we prove two main results. The first is necessary and sufficient conditions for controllability under control bounded by a hard constant. Let all these conditions hold. A state W0 is controllable to a state Wt in a given time t, if and only if W tilde lies in italic H-1, and there exists a control U in an infinity of 0t, such that its norm is not greater than L, and this control U is the solution of infinite Markov power moment problem with coefficients omega n. And the second result is sufficient conditions for approximately controllability under control bounded by a hard constant. Let all these conditions hold. If for each natural n there exists a control un in L infinity of 0t such that its norm is not greater than L, and this control un is the solution of finite Markov power moment problem with coefficients omega n, then a state W0 is approximately controllable to a state Wt in a given time t. In the next chapter, we would like to obtain numerical solutions to approximate controllability problem. For this purpose, we construct an orthogonal basis in this space, italic H-1. Let L and beta be the generalized Laguerre polynomials. Here its definition for n from 0 to infinity and beta greater than -1. As it is known, these polynomials are orthogonal on a half-axis with respect to this weight function, y to the b and e to the -y. For each n from 0 to infinity, we construct a function Cn1 of x that depends on Lp1 of -2t, Lp1 of modulus x squared over 2t, and delta Lp1 of the same argument for p from 0 to n and x lies in R2. And we prove in our work that the system of these functions Cn1 is an orthogonal basis in italic H-1. With the aid of our constructed basis, we obtain necessary and sufficient conditions for approximate controllability. Namely, we prove this theorem. Each state W0 belongs to the space H minus 1 tilde is approximately controllable to any state WT belongs to the same space in a given time t, if and only if W tilde is an element of italic H minus 1. And we also obtain an algorithm for construction of piecewise constant controls, solving this approximate controllability problem, and for construction of approximate states using our orthogonal basis. And the last result is illustrated by the following example. Let t equals 1/2. Let initial state W0 equals this function. And let a target state Wt equals this function in a half plane. Consider controllability problems for control system 2,4 in a half plane with this data. Verifying this condition in the theorem, we conclude that it holds for our data. Therefore, due to this theorem, we conclude that this state W0 is approximately controllable to this state Wt in a given time t. And using our algorithm, we construct piecewise constant controls U and L in this form: the sum over n from 0 to capital N plus 1 over positive constants on 0t. U, n, and L are constants. Index L is from 2 multiplied by n plus 2 to infinity, and capital N is from 1 to infinity. And we also construct approximate states W and L of X in this form. It is the sum of two summand, the first summand and the second summand. And here we can see our control, piecewise constant control U and L. And due to our theorem, we have that the norm in the space H minus 1, 0 circled, of the difference between approximate state W and L at the point T and the target state, our given target state Wt, tends to 0 as n and L both tends to infinity. And we have graphs or figures for this example. These two figures show us the graphs of our difference between approximate state and target state under influence of our constructed piecewise controls U and L. Here the case when n is 3 and L is 50, and here the case when n is 4 and L is 200. And we can see that our difference decreases when n and L both increase. And these figures show us the graphs of piecewise constant control U and L. Here in the case when n is 3 and L is 50, and here in the case when n is 4 and L is 200. We can see the values of our piecewise constant controls in this case and in this case. And we also can see that our control is equal to 0, beginning from the certain point of time. Here this point 5 over 50, and in this case the moment of time 6 over 200. All obtained results have been published in this paper in 2022. Thank you for your attention.